Hello guys, in the previous classes we have discussed Coulombs law and its applications. So basically Coulombs law gives an expression for electrostatic force of interaction between two point charges as K into Q1 Q2 by R square. Now you can apply this expression only for point charges, but in case of distributed charges, as the distance between two charges is not unique, you cannot apply Coulombs law directly. So to find electrostatic force of interaction between a distributed charge and a point charge, we have to divide the distributed charge into very small infinitesimal parts, right? We call it as element. So now we have to pick one element and then find force of interaction between this element which I have picked and the point charge. Now once we got this force, we will use a mathematical tool called integration to add force due to all the elements of the distributed charge. So this entire process we have discussed in the previous lecture in a very detailed way by step-by-step manner. If you have not watched that video, please go through that and you will be very clear about finding force of interaction between a distributed charge and a point charge. Okay, so the next question is how to find force of interaction between two distributed charges. Let us say we have a ring and a rod. Now we have to calculate the electrostatic force of interaction between these two charges. Now here the distance between these two charges is not unique. So if you take this part of the ring, this part of the rod and this part of the ring, the distance will be different from the distance between these two parts. So for each and every part on the rod and ring, the distances will vary. So now we cannot apply Coulombs law directly. So what we have to do? We have to break it. How to break it? So we have to break the rod into very infinitesimally small parts like this, and a rod also we have to break into infinitesimally small parts. Now we have to pick the element. So let us say we have picked an element in the rod dq2 at a distance x from this end of length dx. Similarly, we have to pick one more element here. So we will pick an element on the ring at an angle theta with this axis and making an angle d theta here. So this is what we will take. Now what you will do is, first we will find interaction between this small part of the rod with all the parts of the ring. So the process will be same as the previous process, right? That is a force of interaction between a point charge and a ring. So we can treat this as a point charge and this is ring. So using the same method, you can calculate force of interaction between this point charge and this ring. So once we got that force, now what you will do? Similarly, we will add all these parts, right, due to each and every part on the ring using integration again. So here we have to use double integration to calculate force of interaction between these two distributed charges. So the general representation is like this. So F is equal to double integration of K into Q1 Q2 by R square. So now using this process, we may calculate force of interaction between these two charges, but the process will be very lengthy and we will use heavy calculus here. Okay, so this entire process will become very simple once we discuss a concept of electric field. Here I have discussed this example just to make you understand the significance of electric field and to make you know how electric field concept makes these kind of questions very simple. So we can calculate force of interaction between two distributed charges using Coulombs law by taking elements on both the distributed charges. But here the problem is you have to use heavy calculus because we have to double integrate it. So the major concerns arise while using Coulombs law. The first one is usage of heavy calculus. So just now I told you, right, we have to integrate it twice. So it will make the process lengthy and also difficult. The next concern is it is very difficult to visualize. As it is a non-contact force, it is very difficult to visualize because we come across contact forces in day-to-day life, but not non-contact forces. So when I apply a force directly on this hand, it is easy to visualize it and we can perceive it easily. But when I apply force without touching it, if I pull this one without touching, you will feel it as a magic, right? And one more example I'll tell you, we are always fascinated about magnets. The childhood we are always fascinated about magnets because there the force applied by one magnet on another magnet is non-contact force. As we are not habituated to non-contact forces, we feel fascinated when you see those kind of forces. So here this electrostatic force is a non-contact force, so it is not that easy to visualize non-contact force. So these are the two concerns which arise while using Coulombs law for finding electrostatic force of interaction between two charges. So to make understanding and the visualization of a non-contact force better, they have introduced a new concept called electric field. Basically, we perceive a non-contact force as a two-step process. The first step, any charge produces some field around it. We term it as electric field. And when some other charges enter this electric field will interact with the charge. It means the field will apply force on the other charges. So this is how we perceive a non-contact force. Instead of directly saying two charges directly interact with each other, we are dividing it into two-step process. That is, first a charge produces field in the space, and when some other charges enter this particular field, this field will interact with the charge. So this is how we perceive. Now I'll try to explain it using an example. So you might have seen a spider. So spider produces a web around it. Now when small insects enter this web will apply force on it and the insects gets trapped in the web. Now in the same way, a charge produces a field around it, and when some other charges enter this particular field, this field will apply force on the charge. So here one important point you should know is electric field of a particular charge is always invariant. It means field produced by a particular charge does not depend on other charges around it as well as the medium in which this charge is present. The net electric field in the space may depend on the configuration of other charges as well as the medium in which the charges are present. But electric field of a particular charge does not depend on other charges and the medium in which it is present. So before going ahead, let us look at the definition of electric field. Electric field of a charge is the space or the region around it where it can influence other charges. It means the space or the region around a charge where it can apply force on other charges. The next question that arises is how strong is its influence? So to understand how strongly this charge can influence other charges, what we can do is we can keep a test charge at that particular point. So let us take an example. So this charge produces field around it. Now you want to test how strong this field is. Let us say at this point. So at this particular point I want to test how strong is the influence of this charge. Now to check it, I'll keep a test charge here. So let us say Q0 charge. Now using Coulombs law, we can find force of interaction between these two charges. So now let us say the force applied by this charge on Q0 is some Fe bar. Now this is the force. If this force is strong, the electric field strength will be strong, means its influence is strong. But one problem here, this Fe depends on this Q as well as Q0, but we want to test only the influence of this charge. So to get the exact influence of this charge at this particular point, what I'll do is I'll find this force per unit test charge. Okay, so Fe by Q0 will give you the force applied by this charge on a test charge per unit charge. Now the force per unit charge depends only on this charge as well as the location of this point, but not on this test charge. So that is the way in which we can test the strength of this electric field. So we can define electric field strength or intensity as the force experienced by a positive test charge per unit test charge. So electric field is a vector quantity and it is denoted by E bar. So E bar is equals to F bar, that is electrostatic force per unit test charge. So this is how we can define a electric field strength or electric field intensity. So here there is one more problem. So here, if you take this Q0 charge very large, this charge may influence the field here. So as we discussed, electric field due to this charge is invariant, but net electric field in the space may change due to other charges. Now if this test charge is very large, now this test charge may influence the net electric field in the space, and the result you get may be different from electric field of this charge. So to avoid the issue, we have to take the test charge to be very small. So Q0 has to be very small. So now we will deal with electrostatic interactions in two independent steps. So in the first step, we will concentrate on finding electric field strength due to various charges. That is, by placing a test charge and finding force experienced by that test charge per unit charge. Okay? In that manner, we will calculate electric field due to various charges and we will remember them. And then we will concentrate on finding force due to electric field on different charges. So in the first step, we will calculate electric field strength due to various charges, and then in the second step, we will find force due to electric field on different charges. So in this manner, we can calculate electrostatic interactions. So now let us concentrate on finding electric field due to various charges. So in that, first let us calculate electric field due to a point charge. So let us consider a positive point charge here plus Q here. Now let us calculate electric field strength due to this at a position vector r bar. So at this particular point we want to calculate electric field strength. Now to find electric field strength at this point, we have to place a test charge here. Let us place a small test charge Q0. Now we can use Coulombs law to find force of interaction between these two. So force applied by this one will be Fe bar will be equal to, according to Coulombs law, we can write Fe bar as K into Q naught by magnitude of this is R cube into R bar. Okay, so from here we can say Fe bar as K into Q naught by R square into R cap, that is position vector or unit vector in the direction of position vector. So now we know electric field is given by Fe bar upon Q naught. So from here we will get electric field as K into Q naught by R square into R cap divided by Q naught. So from here we will get expression for electric field as KQ by R square into R cap. So this is expression for electric field due to a positive point charge. Here we can note two important points, two conclusions we can take. The first one, electric field due to a point charge, electric field due to positive charges we can say, is always radially outwards. Because it is R cap. The second point, here we can find it, the strength of the electric field is inversely proportional to R square. So electric field strength is inversely proportional to R square. So these are the two important points we can note. So let us draw electric field due to a positive point charge. So if we consider a positive point charge here plus Q, Now electric field due to this is always radially outwards. So this is how the electric field looks. And it will be symmetric in all the directions. So electric field due to a positive point charge is always radially outwards. Now similarly, let us calculate due to negative point charge. Now if I take a negative point charge here, now let us calculate electric field strength due to this negative charge at a distance r or at a position vector r bar from this point charge. Now for that we will place a test charge, very small test charge q naught here. Now as these two are unlike charges, the force will be attractive force. Okay, so Fe bar will be like this. So again from a vector form of Coulombs law, we can write Fe bar as k into minus q into q naught by r square into r cap. So here electric field will be k into q by q naught you'll have, so q naught by r square into minus r cap divided by q naught. So from here we'll get electric field strength as k cube by r square into minus r cap. So that means here again we can note 2 points. So first thing, it is radially inwards. So this minus r cap means it is radially inwards. So electric field due to a negative point charge is always radially inwards. And the second one, electric field strength is inversely proportional to r square. The first point we can note is electric field due to negative charge is always radially inwards. And the second point, electric field strength is inversely proportional to r square. So these are the 2 points we can note. And electric field, we can draw electric field due to a negative test charge, a negative point charge like this. So it is always radially inwards. So it is always radially inwards. And it will be symmetric in all the directions. So this is how electric field due to a negative point charge looks. We understood that electric field due to a point charge is inversely proportional to square of the distance from the point charge, and electric field due to a positive point charge is always radially outwards, and electric field due to a negative point charge is radially inwards. Now if we have multiple charges in the system, what will be electric field at any point? We already discussed that electric field due to any charge is unique and it does not depend on the medium and the charges around it. But net electric field at any point in the space depends on all the charges in the system. So now how to calculate electric field at any particular point when we have 2 or more charges in the system? Similar to electrostatic force, electric field can also be found using principle of superposition when we have multiple charges. According to principle of superposition, when there are 2 or more charges in the system, then the net electric field at any point is given by vector sum of individual fields at that point due to all the charges in the system. So let us see for example. Now let us apply it for few examples. Let us consider a situation where we have 2 identical charges q each on vertices of an equilateral triangle of side A. Now let us calculate electric field at this vertex A. Now to calculate electric field, net electric field at this point, first we have to calculate electric field due to individual charges. Now let us say electric field due to this charge E due to C is in this direction, electric field due to charge at C. is given by K into Q by R square. R is A, so KQ by A square. Now electric field due to the charge at B will be in this direction, as it is a positive charge radially outwards. Okay, now electric field due to charge at B will be K into Q by, again distance is A, so A square. So both are equal, magnitude is equal, so let us say both are equal to some E, and here also let us denote it by E. Now if I write it at this point, two vectors E and E, angle between these two. So let us, we know angle between any two sides in an equilateral triangle is 60 degrees. So now if this is 60, this angle will be 60. So if I write it here, so we have E and E, two identical vectors are separated by an angle 60 degrees. Now we know the resultant of two vectors is given by under root of E1 square plus E2 square plus 2E1 E2 cos theta. So let us apply it. So E square plus E square plus 2 into E1 E2 will be E square into cos 60. Cos 60 is 1 by 2, so 1 by 2 and 2 gets cancelled. So it will be 3E square. So net electric field, magnitude of net electric field will be root 3 times E. And so net electric field is root 3 times KQ by A square. So this is how to calculate net electric field. And the direction will be, as these two vectors are identical, then the resultant will be at angular bisector to these vectors. Okay, so this is the direction of net electric field and this is the magnitude. This is how to solve this kind of questions using principle of superposition. Now let us apply it for few examples. So first case, let us consider two identical charges located on the vertices of equilateral triangle of side A. Now let us calculate electric field at this vertex. And now to calculate electric field at this point, first let us calculate electric field due to these two charges individually. Let us say this is charge 1 and charge 2. Now electric field to this one will be in this direction. Due to point charge, positive point charge, electric field is radially outwards. And let us say this is E1 and it is equals to K into charge is Q by distance is A, so KQ by A square. Now similarly, due to this charge, electric field will be radially outwards again. It will be in this direction. So it is E2 and the E2 value is equals to K into Q by A square. As both values are equal, let us say both are equal to E, denoted by E. Now if I write it, the two vectors, electric fields are vector quantities, so E and E in this direction. And we know angle between any two sides in a equilateral triangle will be 60 degrees. If this is 60 degrees, this will be 60 degrees. Now angle between these two is 60 degrees. So resultant of these two can be found by vector addition, that is E net is equals to, or E resultant is equals to under root of E1 square, that is E square, plus E2 square plus 2E1 E2 is also E square. Cos of angle between them, what is the angle? 60 degrees, so cos 60. So cos 60 is 1 by 2. So you will get net electric field at that point as root 3 times E. That is, net electric field at that point will be given by root 3 into KQ by A square. So this is how to calculate net electric field. And the direction will be in this direction. As these two are identical, it will be angular bisector of these two forces. Next, let us consider a situation where we have three identical charges on vertices of a square. So Q, Q and Q. And let the side of the square be A. So this distance will be A and this distance will be A, and here also it is A. Now let us calculate net electric field at this fourth vertex. Now for this we have to calculate electric field due to individual charges at this point. So electric field due to this charge will be in this direction. As it is positive charge, electric field will be radially outwards. and electric field will be equal to K into Q by distance is A square. Now if you calculate electric field to this one, it will be radially outwards in this direction, horizontal, and its value also is equals to K cube by A square. Now if you calculate electric field due to this one, the distance between these 2 points is root 2a, okay, and it will be along angular bisector. So this angle is 45, so this angle is also 45 and this is also 45. Now electric field due to this charge will be K into Q by distance is root 2, so root 2a, so it will be root 2a whole square, so 2a square. So electric field due to this charge will be in this direction, it is kq by a square. Electric field due to this charge is in this direction, electric field is in this direction. Now let us say kq by a square as E. So this is also E and this will be E by 2. Now if I write these two values at a single point, so electric field E in this direction, E in this direction, and E by 2 along angular bisector. Now let us find resultant of these two first, and resultant of these two will be along angular bisector because these two are identical charges and it will be equal to root 2e. So net electric field will be equal to, if I take E common, it will be 1 by 2 plus root 2. So that is, from here we'll get net electric field as K cube by A square into 1 by 2 plus root 2. So this is net electric field. Now let us consider three identical charges on vertices of equilateral triangle of side A. And now let us calculate net electric field at the center of this triangle, equilateral triangle. Okay, now let us calculate first electric field due to individual charges. We know this distance will be A by root 3, and this is also A by root 3, and this distance also will be equal to A by root 3. Now electric field due to this charge will be radially outwards, it will be in this direction, and electric field due to this will be in this direction, and electric field due to this will be in this direction. Now as three charges are identical and the electric field will also be identical, so let us say it is E, and here also it will be E, and here also it will be E. Now value of E is K into Q by distance is A by root 3, so A by root 3 whole square. Now we want net electric field at this center. So for that, so these are the three forces, E acting downwards, E in this direction, and E in this direction. So these are the three fields acting on it, three vectors. Now we have to calculate vector sum of these three. Now let us calculate the angles first. So we know this triangle will be right angle triangle, and this angle we know in a equilateral triangle it will be 30 degrees. So if this angle is 30 degrees, so this angle will be 60. Similarly, this is also 60. So this total angle is 120. Similarly, three angles will be 120 each. So 120, 120 degrees, and 120 degrees. So these are the angles. Now we know, according to Lamb's theorem, when F1, let us say F2 and F3, we have then F1 by sine theta 1 is equals to F2 by sine theta 2 is equals to F3 by sine theta 3. Then this particle will be in equilibrium. Now similarly we have three electric fields. Now net value of these three vectors will be 0 because E by sine 120, E by sine 120, E by sine 120 is same. So net electric field acting on this point will be 0. Next situation, let us consider four identical charges Q each on vertices of a square of side A. And let us calculate net electric field at the center of the square. So this is diagonals. So at this point let us calculate the electric field. And a simple question. So we know electric field due to this charge will be in this direction and electric field due to this charge will be in this direction. As these two are identical charges and the distance will be same, so electric field due to this one, if it is E, here also it will be E, that is this value will be K into Q by A by root 2 whole square. And similarly here also K into Q by A by root 2 whole square. So these two electric fields cancel. And similarly these two electric fields cancel. So the net electric field at the center of the square is also 0. Net electric field is 0. Similarly, let us consider one more situation. Let us consider a regular hexagon. So let us consider 6 identical charges Q each on vertices of this regular hexagon of side A. Now let us calculate net electric field at the center of this hexagon. So here also electric field due to this one will be in this direction, electric field due to this in this direction, and the distance everywhere it will be equal to A in regular hexagon. So all these sides will be A. Now if we calculate electric field due to each and every charge will be same and they will be in all the directions. So this electric field and this one due to this charge and due to this charge cancel each other, and due to these opposite charges electric field cancels, and due to these two charges electric field cancels. So again net electric field at the center will become 0. So here we can note that net electric field due to identical charges placed on vertices of a regular polygons at center will be always 0. That is triangle, first case we discussed for triangle. So when you have 3 identical charges on vertices of a triangle, then also net electric field at center is 0. And similarly for square also it is 0, and for hexagon it is 0. It's not only for triangle, square and hexagon, it is applicable for any polygon, regular polygon. Regular polygon means all sides are equal and all the vertices will be lying on a circle. Such kind of polygons are called regular polygons. So if identical charges are placed on vertices of a regular polygon, net electric field at the center will be always 0. Now let us see one application of this. Let us consider a regular pentagon. So let us place 4 charges on the vertices. Let us say this is lying on a circle of radius r. So let us say the circle is of radius r. Now there are 4 charges Q each on vertices. Now we have to calculate electric field at the center. So pause the video and try to solve this question. So now, as we know, net electric field at center when identical charges are placed on all the vertices of regular polygon will be 0. Here we have only 4 charges, we don't have a charge. So what I'll do is I take this 0 charge as sum of Q and minus Q. So minus Q plus Q gives you 0 charge. So now we know electric field, net electric field due to these 5 charges at the center will be 0. Now only part left is this one. So if we calculate electric field due to this minus Q charge, we will get net electric field due to these 4 charges. Okay, so due to negative charge, electric field will be towards it radially inwards in this direction, and we know this side will be R. It is given as R. So electric field at this point will be K into Q by R square. So this is how to calculate net electric field.
Guys, if you find this video helpful, please hit the like button. In this series, I'll cover entire JEE syllabus. And apart from physics lectures, we will be coming up with exciting videos on career guidance, like review videos on engineering colleges and detailed analysis of all branches. And we are also planning to share informative videos on entrepreneurship. So if you don't want to miss out on these videos, please subscribe to our YouTube channel.